So first, now that we know that we can calculate the derivative with the limit, what we're going to do is, since we can obtain a function thanks to that, we're going to obtain the function for a bunch of functions that that we can use as basis to calculate then further derivatives. First of them is going to be the constant function. The derivative of the constant function is going to be 0. And it's easy to see because this is a constant line here, and the slope of the tangent line is just going to be another line with no slope. So this is going to be 0. It's really easy to see in the calculation that that's the case, because if you consider f of x equals certain constant, f of x plus h is also going to be that constant. And so the limit when h goes to 0 of f of x plus h minus f of x over h is nothing else but c minus c. Okay, and so that's going to produce a 0. And it's going to give us the function of the derivative of that constant. So for any constant that we have, we're going to have that the derivative is 0. Okay. Now, this is going to be the first rule that we're going to establish. Derivative of any constant, 0. Now, let's move on to powers. If you have a power function, is the form x to the n, where n is a non-negative integer. And the rule for powers is going to be, if you have x to the n and you take derivative, then you're going to get n times x to the n minus 1. This is a little bit more difficult to prove via limit, so we're just going to establish this function. You can prove it really easily with functions like x squared or like x cubed, but going higher is going to be a little bit more cumbersome by limits. So that's why we want to establish this formula. You can really easily see some examples of this. So if f of x is x to the n, then the derivative is supposed to be n x to the n minus 1. And so as examples, if f1 of x is, well, the constant, which can be considered x to the 0, then you can see that f1 prime is just going to be 0, which is essentially 0 x to 0 times x to the 0 minus 1. Okay, so it holds the rule. Not that necessarily we want to do that. If f of x is x, then f prime of x is going to be put down the 1, which is here in the power, and then it's going to be x to the 1 minus 1, so 1 times x to the 0, so 1. So the derivative of x is just 1. Now we can follow this pattern, and the derivative of f3 when being x squared is now going to be 2x, and similarly x cubed is now 3x to the 3 minus 1, so 3x squared. Okay. Now another example will be, consider the function x to the 9. So we're going to put down the 9, and we're going to subtract 1 to the power, so it will be x to the 9, 9x to the 9 minus 1. The derivative of 5, then it will be 0. The derivative of x will be 1. And the derivative of 2 to the 9 will be 0, because that's still a constant. Okay? So let's just remind really quick over here this is an area. So for the first one, derivative, this is another way of writing the derivative, by the way, of x to the 9 will be 9x to the 9 minus 1 or 9x to the 8. Derivative of 5 will be the derivative of a constant, 0. Derivative of the function x will be 1. And notice that this is equivalent to dx, so kind of makes sense that it's a 1 in this notation. And now 2 to the 9 is a big number that I don't know at this point. You can use your calculator to know what it is, but it's going to be a constant. So that's why we always get that this is 0 regardless of having a power. So don't be confused by that. Now, when we have constant multiplying functions, a different situation is going to pan out. And what we have is that the derivative of the multiplication of the constant by the function is just going to be the constant multiplying the derivative. Another important rule is that if we have the sum of two functions, then the derivative of the sum is just going to be the derivative, the sum of the derivatives. And then thanks to that, we can apply these rules to different functions and do more complex derivatives. So let's take a look to the derivative of minus 7 over 8 x cubed, 5 times the square root of x, and x squared plus 2x plus 3, and 2 plus 3x. Okay? So let's do that here in the board. So notice that this is the scenario where we have a function multiplying a constant. So we can just put out the constant and keep the derivative. And so we obtain the derivative after that. So in this case, that's going to be 3x squared. And so we can multiply at this point minus 21 over 8x squared. Okay? And the next case is similar. We have the derivative with respect to x, 5 square root of x. And so that's going to be 5 times the derivative with respect to x of square root of x. And that's just 5. And the derivative of the square root of x is 1 over 2 square root of x. Okay. Remember that this is a power, so that's where we get in that. But let's check that into details. Okay, so square root of x is x to the 1/2, right? And so the derivative of square root of x is the derivative of x to the 1/2. So now we're using the power rule here. And so if we use the power rule, we put down the 1/2, and we put 1/2 to the minus 1. Okay. That's going to yield 1/2 times 1 over x to the 1/2. Because 1/2 minus 1, well, let me just do all the steps. This is x to the minus 1/2. Okay? And so the minus in the power is just going to be 1 over x to the 1/2. And so if I multiply these two together, 1 over square root of 2 of x. Okay? So that's where this is coming from. And in general, it doesn't matter that we have a rational number here. We can use the same rule of the powers. Now let's continue with the next example. We had the derivative of x squared plus 2x plus 3. And so the way that this is going to work is this is a sum. So we can just consider this the sum of the derivatives. And so we apply derivatives to each and every single one of the pieces. And we calculate the derivative then at that point. So derivative of x squared is 2x. Derivative of 2x is going to be 2. The derivative of x, which is 1. And the derivative of 3, which is 0. So at the end, 2x plus 1. Finally, similar to the one before, we have the derivative with respect to x of 2 plus 3x. So we can see this as the derivative with respect to x of 2 plus 3 times the derivative with respect to x of x. So this produces a 0 here, and this produces 3 times 1. So the derivative of the whole thing is 3. Now, moving on. First, let's talk about the number e. If you don't remember the number e, you probably saw it in calculus. This is decimal number that is non-periodic. It's an irrational number. And it's 2.71, 828, 182, 8459, and you have a bunch of more decimal quantities over here. This particular number satisfies that the limit when h goes to 0 of e to the h minus 1 over h is 1. Okay? Notice that this is pretty much the derivative at the point 0. This is what we're talking here. The derivative of e to the x in 0. And is going to be 1, which is essentially the same thing that if you block 0 in here. And so what that's going to imply, or later is going to produce, is the fact that the derivative of the exponential function is itself. Okay? Notice if you take a look at the limit, f of x is e to the x. So f of x plus h is e to the x plus h, which is e to the x, e to the h, right? And so notice that when you do the limit of the derivative, this is e to the x plus h minus e to the x over h. Notice that you can really think of it as e to the x limit when h goes to 0 of e to the h minus 1 over h. And since this limit is 1, then the derivative in general is going to be this. Notice that this e to the x is not affected by the limit, and so that's why we can do this. Of course, this is knowing that this limit is 1, which is extra information that we're not going to prove here, but is good to know. We can come back to it later. All right, so the rule here will be that the derivative of the exponential is still going to be the exponential. Okay? Thanks to that, we can now do a little bit more complex examples. So now let's do the tangent line. Let's get the equation of the tangent line at the function f of x to x minus e to the x divided by 2 at the point 0 minus 1/2. Okay? And so let's do that on the board. So first, I'm going to take a look at the function. F of x is to x minus e to the x over 2, and the point is 0 minus 1/2. Okay. All right. So now we can apply the rules that we know. Rules of the derivatives tell me, okay, f prime of x, this is a sum. So I can do sum of the derivatives. So derivative of 2x is 2 minus derivative of e to the x divided by 2. E to the x divided by 2 can be seen as 1/2 e to the x, notice. And so the derivative of e to the x is e to the x. This is going to remain the same. And so the derivative is going to be this same thing. Okay. Now, this previous function in 0 was 1 minus 1/2. Now, if we're going to get the slope of the tangent line, we're going to plug f prime in 0. And so now that's going to be just 2 minus 1/2. E to the 0 is 1. And if we put this together, 2 is 4/2. And so minus 1/2 is going to be 3/2. So now I got the equation of the line. Equation of the tangent line is y minus y0 equals mx minus x0. I have that y0 is minus 1/2, m is 3/2, and x0 is 0. So now that implies that y is 3/2 of x, and then minus 1/2 over here. Okay, and so that'll be the equation of the tangent line on that point. Notice that the fact that we can make the derivative so quickly now, it simplifies a lot of the previous process. Now you can see here how the function is going to behave. This is the 2x minus 1/2 x equation. And at this point, we're checking how is the tangent line. So it's exactly this line over here. Okay. Now let's do another example and use a little bit more involved function. Let's use a polynomial function. With f of x to x cubed minus 15x squared plus 24x, we want to know what values of x make the tangent line to have a slope of 6. Okay, so this is a different question from the usuals. We have f of x to x cubed 15x squared plus 24x. So they're talking about the tangent line to the graph has a slope of 6. So we can find out f prime of x. So f prime of x is now 6x squared minus 30x plus 24. Notice that they're all factor of 6. So 6, and so this is now x squared minus 5x plus 4. So the question is, when is this going to be 6? When is the slope of the tangent line? But this is f prime of x. So we're assuming there is x0 so that f prime of x0 is 6. Okay? But that will be 6 x0 squared minus 5x0 plus 4. Okay? So this means solving this equation. So now I get to cancel 6 because it's on both sides. And so I get 1 should be equals to x0 minus 5x0 plus 4. And so if I move this to the other side, I'm going to get a quadratic equation that I can solve. Okay? And so at this point, then I cannot have a easy factorization here, because there's nothing that multiply gets me 3 and the sum gets me minus 5. So this is something that I can solve by the quadratic formula. So x0 is minus b, which is 5, plus or minus b squared, which is minus 5 squared, minus 4 times 3 times 1, which is a, over 2. And so now this is going to be 5 plus or minus, and this here is 25 minus 12 divided by 2. And so this is 5 plus or minus square root of 13 divided by 2. And so any of these two results is going to work. Either 5 plus or minus square root of 13 over 2, or 5 minus square root of 13 over 2. So this is a quadratic. Okay? And so that's exactly what's happening. This is going to give me these two values, the 0.697 and the 4.303. Those are two values where the slope is exactly 6. Okay? Now, you can continue doing higher order derivatives. So you can take the derivative of the derivative, and the derivative of the derivative is going to be called the second derivative. Okay? And then you can take another derivative, that's going to be the third derivative, fourth derivative, fifth derivative. And in general, if you take the derivative to the n minus 1 derivative, that's going to be the n derivative of the function. Okay? And just to finalize here, let me give you a quick example of a function in multiple derivatives. So consider f of x, the function x to the fourth. Okay, so f prime of x is 4x to the 3. f2 of x is going to be 12x to the 2. f3 of x now is going to be 24x. f4 of x is going to be 24. And f5 of x is going to be 0. And from there on, for n bigger or equals than 6, f of n of x is going to be 0 for this function. Okay. There are scenarios where there's nothing that's going to change. So for example, if you do f of x equals e to the x, well, in general, f of n of x is always going to be e to the x regardless of what derivative you are. And of course, they can be functions that very quickly can go to 0, or that they can take more time to get to 0. Right? Okay, that's all for part 1 of this section.